Okay, so in this problem, we will be analyzing something called siphoning and what causes uh, the pressure to drop the water pressure to drop to the pressure vapor at this point of maximum elevation, and that is something called cavitation. So if the local pressure P becomes smaller than the vapor pressure of the fluid, then it is called cavitation. So what that means is because the pressure at that location is smaller than the vapor pressure, the fluid will suddenly there will be a nucleation of bubbles at that location where the pressure is falling below the vapor pressure. So cavitation is very common in turbine blades where we basically have a very high speed flow. So what Bernoulli equation tells us that P plus half rho V square is constant. So in a turbine blade, let's say if the velocity is very high, then from Bernoulli equation you can see if velocity is very high, then pressure must be very small because this sum is a constant. So so if the velocity is high enough, then the pressure near the rotor blades can sometimes fall below the vapor pressure and cavitation might occur. So because of cavitation, there are instantaneous bubbles like this on the rotor blade, and they break with a very high intensity, thus damaging the blade. So in turbines and jet engines, let's say we need to be uh, when we careful when we decide the velocity. But in this case, uh, in this siphon, the velocity in this pipe is velocity in this pipe is constant because it is the same mass of fluid flowing through all the sections. So, and assuming the cross-sectional area of this pipe is constant throughout, the velocity of the fluid will be the same. But then what is causing the cavitation here? So in this case, Bernoulli equation is P plus half rho V square plus rho gz is a constant. So if my velocity is constant, I can remove this, and this this will boil down to pressure plus rho gz is a constant. And now you can see if we increase z here, because this sum is a constant, that means your pressure would decrease. And if we increase the z to a very high value, then your pressure might fall below the vapor pressure, thus causing cavitation in the siphon. And here it can happen only at this topmost point where the elevation is the highest. So let's see what are the conditions for cavitation in this siphon. So I will first mark various points where we are going to apply Bernoulli equation. So this is point A, then point B is this topmost point, and point C is finally the point where water is discharging into the atmosphere. So first, let's check whether the assumptions required for Bernoulli equations are satisfied or not. The first one is inviscid flow. So here, as I mentioned, the velocity in this pipe remains constant because it's the mass flow rate is constant, and we are assuming a constant cross-sectional area. So there are there are no significant velocity gradients. So there are no viscous stresses per se. So this assumption is valid. Then second is incompressible. This is also true because the fluid under consideration is water and liquids are incompressible. Third is steady. This is also true because again the velocity is constant and we will assume this tank to be very big such that the velocity through the pipe remains constant. And because this H tank is um, decreasing very slowly. And fourth, now we can apply Bernoulli equation along a streamline. So let's choose a streamline. I will choose a streamline which originates at A, then goes somewhere in the fluid, then enters the pipe, goes through B all the way to C and comes out in the atmosphere. So this is my streamline. And now first apply. Okay, before applying Bernoulli equation, let's just write down the pressure, velocity, and elevation at each point. Uh, so PA is nothing but P atmosphere, and which is also equal to the pressure at C because the point C is open to atmosphere. Then VA is negligible; it is close to zero because we are assuming this tank to be very large. So the velocity of this interface is very small. And let's say this is my z equal to 0 location. So this is z equal to 0. So what that gives me is ZA is H tank, ZC is minus H end. So Z is positive in the upward direction. And at point B, the pressure we will assume it to be vapor pressure because we are trying to find out when will cavitation occur, at what height the at what height H hill the cavitation will occur. So to find H hill, we will just assume that the pressure here is the vapor pressure, and velocity at B is equal to velocity at C. It is the velocity at which the water is flowing through the pipe. And finally, ZB is H hill. Okay, with that, so again, if you look carefully, among all these, the elevations for each point are known, pressures are known. What's unknown is the velocity with which the water is flowing through the pipe. So let's just see if we can solve for the velocity of water flowing through the pipe. And we can do that by applying Bernoulli equation between points A and C. So Bernoulli equation tells us that P plus half rho V square plus rho G Z is constant. So PA plus half rho VA square plus rho G ZA is nothing but PC plus half rho VC square plus rho G ZC. So just substitute values from here to here. What you will get is PA and PC are both equal to atmospheric pressure. So they get cancelled out. V is 0, and Z Z A is basically H hill, sorry, H tank. So this is equal to half rho VC square plus, and GC is nothing but minus H end. So solving this equation, we'll find out that VC, which is also equal to VB, is basically square root 2 times G H tank plus H end. So basically, this is the velocity of velocity at which the water is flowing through the pipe. Now, the second step is basically finding out what this H hill is, such that the pressure at B is the cavitation pressure. So to do that, let's just apply Bernoulli equation between point A and point B along the streamline as I showed. A and B. So PA plus half rho VA square plus rho G ZA is PB plus half rho VB square plus rho G ZB. So again, PA is atmospheric pressure, PB is vapor pressure, because we're trying to find out H hill such that the pressure cavitation occurs at B. VB is nothing but this formula, and ZB is H hill, ZA is H tank, and VA is 0. So Bernoulli equation between points A and B gives us PATM plus rho G H tank equal to vapor pressure plus half rho 2G H tank plus H end plus rho G H hill. So again, if we solve for H hill, we'll find out that H hill such that the pressure at B is vapor pressure and cavitation occurs is PATM minus PV divided by rho G minus Hn. So if we elevate the pipe to this height, then basically cavitation will occur at B and the flow through the siphon will stop. So once cavitation occurs here, the flow breaks down, and then no flow occurs in the pipe. So we need to be careful such that the maximum elevation in a siphon system should be smaller than this value.